Oh, there's somebody else coming in from our side. So they. Okay, that's hello.
Hello.
Hello. And I will mostly. Well, question is, I think we could just go into the software directly, or do you want something? Some more introduction stuff.
Yeah. This is Joseph Kim. I'm Joseph Kim. I am technical stage director in Master Korea. So, you know, we have a little bit hard to pre-processing hyperspeed cameras. So I request to SOS for pre-processing. So, yeah. And another person is our co-worker. So we wanted to training today together.
Yep. And it's really the software training what you want. And so I think I will walk you through how to work with the software. Is this correct?
Yeah, correct.
Yeah. So you don't need an introduction to Parge.
Yeah.
No need for an introduction.
Right.
Yep. I think I'm gonna share my screen mainly, and let me see which screen I have. Guess I will share that one. Okay. Yeah. So now you can see the screen, isn't it? Yep.
Yeah.
Yep. And can you read the menu? Is it sharp enough? Can you read the software?
Yeah.
Can you read it? Is it okay?
Yeah. Perfect.
Yeah. It's okay. And so I tried with your data already yesterday, and well, it's not perfect yet. So one has to think about it. There are some problems with the data, and I will show you where the problems are and how far we can get based on the current state of the data, and then we have to think about how to improve it further. That's the point. And so the first thing is to import it. So we can we always start importing the data. For Shark, it's under various down here. And you have the Shark sensor, and I'm selecting the image. You already provided BSQ files, so I'm selecting that one. One could also take the BIP file or the HSI file, and it would convert it directly to BSQ. So BSQ is pan-sequential, and in Parge we always work with pan-sequential data. So it's a standard. Now for the coordinate conversion, one can we're needing the Korean system. So one can select EPSG standard for the coordinate system, and then one can search for Korea, and it will show all Korean system, maybe 2000, and I think it's one of them. I don't know which one is better. I think they're a synonym.
Yes, first, second one, yeah.
So you see down here the EPSG number down here.
Yes.
So it's 5186 or
5186. Right. Yeah, that is right. Yeah.
That's the correct one. So we would import that one at first, and then we got our data ready. So seems to be correct. Second thing is to load the digital elevation model. So first the data, then the digital elevation model. And we just can have a look at the image, so display image, file display image, then you can see the digital elevation models received from your side a DSM. that's somewhere. Where is it? Further down. No, it's not here. It's just put it that way. Sometimes you have to change the filter to see everything. So here it's the DSM. Here it is, and one can load the DSM directly, and can have a look. Can have a look at that one. And if you look at the DSM, it's quite rough, as you see.
Mm-hmm.
So the trees are not really mapped in detail. So there's very little detail in the DSM. So this will be hard to get good results based on this digital surface model, because it's just a little bit too coarse if you look through these trees. So this DSM is, I guess, it's coming from Pix4D.
All right.
Yep. That's one thing. So, so one has to think about if one wants really to use that one, because he will get artifacts for the trees with this kind of borders. Or one can go, fallback solution is to go for a flat DSM or the DTM for a digital terrain model instead. Or one could, well, in hyperspectral, many people are using LiDAR to create a DSM at such high resolutions, but I guess you don't have a LiDAR available. So that's the first problem we had. So, and we can I can import that one. Import. You can import it as a GeoTIFF, and then it will write an env file. So in Parge, we always want to have env files for the processing. So we should import it if it's a TIFF, and then create an env file from it. So if I'm importing it, where is the DSM again? I can't see it anymore. DSM. Here it is. We has to write a filter, and now we have to provide a name for it. And I just use the name ele.bsq. That's standard I'm often using. So I will all write that on because it's the same file. And so that's how you get your elevation data. This error is the background is apparently minus 9,000. This will be set to 0, so it's not a problem, this error message. So that's the DM. There is to get a flat DM, that's an alternative, but we can look into this later. One can also fallback, always import a global elevation model. So this means one just takes the average altitude of the ground and uses that one for the processing. So that's an alternative. So I could import the global. So this is from the global data. I don't know if you installed that one, by the way. So the global elevation model is to be installed through the help menu. Install add-ons here, and then you see there is the GMTED elevation data. That's the one I often use. It's a very rough elevation model. It's 100-meter resolution, but it gives you an idea of the ground altitude. So that's so you would need to install it through the help menu if you don't have done that yet. So it will be downloaded directly. Or you could provide an own DTM, of course, from your mapping agency or wherever you got it from. And here, if you import, we're working at 2 centimeter resolution. So we have to reduce the resolution. So we would interpolate it maybe to 5 meters or maybe 1 meter, such that we have a or maybe 2, so such that it fits somehow to our data. Otherwise, you only get 2 or 3 pixels if you take 100 meters. So here you should really increase the resolution. Here, you take the same coordinate system and you define the name of the global LA, and I can use that one, global LA.bsq, and create the DEM. And if you look at that one, of course, it's very simple. Display DEM, it's just a trend data and nothing else. It's just a 240 meters, kind of between 244. So now that we have the image data and the digital elevation model, I always make the check in auxiliary. I go down to plot image area here, and here I can see how the image will look like in the end. So here I can have a check if it's correctly loaded and if it makes sense. The dash out here is the range of the DSM, which is larger, but it fits within, so it seems to be okay. Now, now we can further checks to do. So currently I'm talking about experimental use. I can go should go into the filtering. I usually go into filtering, then I can check out the parameters. So auxiliary, that was auxiliary filtering. And I can look into all the parameters like the roll. How does it look like? The pitch seems to be okay. The heading. If I click into it, it will zoom to some portion of the parameter. The roll, pitch, and heading of the IMU data seems to be okay. Now, if I'm looking at the x coordinates, we have a problem. So the GPS apparently renders very jumpy data. So if you look here, you can go anywhere. We always have these jumps in the coordinates. The same happens to the y coordinate. You all have these jumps, or in the height, we also have some jumps, but strong jumps. You even see it roughly here. So apparently the GPS of this system is very low accuracy. And well, so what can you do about it? The only thing we can do is smooth it out. So that's something we could do during data import, but maybe I should check it. We can also do it here. So we could just go into here and smooth it. Maybe factor it was about 30, such that you don't have these gaps anymore. So yeah, that's a manual thing. What one would need, I guess, at some point, if this is always the problem. So if you can't find a solution for GPS, then one would need to update the import filter such that such smoothing can be done automatically. But that's currently so for the experimental thing, I had one has to do it manually. Save. I go to the x coordinate. I'm also smoothing it. Save to the y coordinate, smoothing it. X, y coordinate, smoothing it out. Save. So this is not smoothing is not a big problem for GPS because this has to be smooth. It's always continuous, so you don't have a big variation. So this is smoothed out now. This was a second problem. So we have 2 problems so far. First problem, the digital surface model. The second problem, the parameters, the GPS parameters. Now I can go into the image area again. Okay. This can be closed. Now that have loaded everything, I'd do a first processing. So I go directly into the direct processor, and I'm currently I'm only processing 3 bands because this is a test. So I don't do the whole image. I can just use a default RGB display. And using the global elevation model now, I can show you afterwards what happens in between. And the output pixel size I put to 2 centimeters. I don't know what's your target pixel size normally? Is it 2 centimeters?
0.7 centimeter.
7 centimeter is your target.
0.7 centimeter.
0.7.
Yeah.
Okay, yeah. One could do this later. So for now, I do it if one could do it to 0.1, then to 1 centimeter.
Yes.
Now. And I always choose fast nearest bilinear, and then it will create an image. I don't run it now because it takes about 5 minutes. So I can show you the result already because I did it before. And this is what you get. There are various outputs I got here. There is the first trial was that one. This one was without smoothing parameters. That one. Well, let me see. Oh, that's I'm no, sorry. I think that's Let me see how it looks like further down. Yeah, here we have problems. You see. So the no smoothing was done, and here we have the problem with the. I think it was even the wrong. It was a surface model. That's why you get these gaps. You see this gap?
Yeah.
Because it was using here again. So I was using the surface model for this processing, and so the quality is quite low. So you have these artifacts from the surface model, and you have some jumps in the image that comes from the jumps of the data. So that's just how it would look like without doing some adaptations. I'm now going into the one with the bar sighted. Yeah, let's take that one. This one is already a little bit better. Still, you see up here, still, this is the bar sight. So I already show you the bar sighting afterwards, how it's done. But it was also processed with the digital surface model. You see these gaps. So because the tree is just elevated and it's a straight line of the surface model. So I think it doesn't make much sense to use this digital surface model here. If you look at that, I think one has to go for the flat ground. So that's why I chose to use a flat or a digital terrain model. While I only had this global elevation model, I guess you will have a better one available somewhere. So digital terrain model from Korea, there must be available somewhere. So you could search for such a one and use this one for the processing. So now I'm gonna show you the one. The best result. I'll show you afterwards how I came to that one. That's this one. And so this is done with a flat terrain model, so with the global one. And it's also up here, it seems to be square again, so you don't have these artifacts. And if you're going down further, also this one is nice. And we have down here, we don't have jumps in this roof anymore. But it's something still seems to be not perfect, so we have distortions. And that's something else to check out now. That's yep. So how did I how to do the so-called bore sighting. I'm gonna restore a status. By the way, in Parge, if you're working on something, you can always save your current situation by save status. And then you can, I call this a GCS file. So you can name it any GCS file, and it will store your current working situation. This is also stored automatically if doing an automatic processing. And so whenever there is a problem, you can go back to a former situation, or you can also, if you need support from my side, I always ask for this GCS file, so this geocoding status file, because that one tells me everything about the current status of what's going on in the data. So I'm going to restore such a status, and I use the one before. Okay. Okay. So it restored also the digital elevation model. Let me see what digital elevation model we have. I think we have now that one. So I want to change that one. Just a moment. I use the global. I use this flat 20 centimeters global elevation model. And now I want to do the so-called bore sighting. Bore sighting means system calibration. So I want to calibrate it against a reference. And you provided a orthophoto from Pix4D. So one can use the orthophoto as a reference to yep, I already have some GCPs to get it done. So I'm doing, there are various possibilities to do the bore sighting. One is the traditional way you collect GCPs against each other. So you need about 20 GCPs, ground control points, between the orthophoto and your image. You can also do automatic bore sighting, but for this you'd need a good stable reference. So over trees, this will not work well. So if you have these trees, it's matching won't work. And so for the automatic bore sighting, it does a matching between the orthophoto and your image. And so if you want to do a good bore sighting, you should fly your system once in a while over some settlements or some roads, such that it's stable. You have good structures to do a matching between an orthophoto and your system. Usually, the so-called bore sighting is only to be done once in a while, so every few years. So if you once have good bore sighting, you wouldn't need to change it. So that's not to be done every time. So that's what the problem is, to get it once a good one. So let me see how this works. Let me show you how this works. So I go to collect GCPs. So I do this. That's the manual way to do it. It's still usually the most stable one. I have now the rectified image. So I did a first run of rectification before. So it was just a preliminary rectification. And then this can be, so this is already rectified but not geocoded. So you can have it's much better to search for GCPs if you have a rectification done. In here, I got these ground control points. This one was based on the digital surface model, but you could also do it on the flat ground. So you have a few points I already have searched before. And then at the same time, you load the auto image. that one. That's the other image you provided. Here are the ground control points over here somewhere. You have to, so here you see them. And now you can put them one beneath each other, such that you're trying to squeeze it onto the screen. So big screens are always nice for that. So now you can are able to search corresponding points in the data. So you get a new point, for instance, just you maybe you go here and just say, well, this should be my new point. So I say push position. It will show a mark. So this is in this image, it's found. Then I go over to the other image. This was somewhere here. It seems to be, well, it's hard to find, but I'm just assuming that it was somewhere up here. Oh, can't find it. Maybe it was not the best sample. Maybe I should start here from that one. I'm taking that one. Push position. Here again. Push going a little bit further up to that one over here. Going in. Here I have it. I assume that it was that one. It's not. It's quite hard to get a good ball sighting point with this data. So I would say push position. And after I've found the point, I push here get and add point. So it will load the point into the list of GCPs. Now this was the 17th. I already had 16 before, and then it will be stored. And then I can always show the list, the ground control point list. So that's this one. This list shows the pixel and the line coordinates of the image, of the original image, which is indirectly loaded from the data. Then the coordinates, the absolute coordinates for each point, altitude of the points, and the offset, or the offsets in pitch, in roll, pitch, x and y direction. So this is 3 meters off. It's quite an offset from in the beginning. If you talk about 7 millimeters resolution, 3 meters is somewhere completely else. So one can now try to do this an optimization, and I'm doing an offset attitude and offset GPS. So I'm doing it manually here. You see the angular difference. It's 4 degrees for the roll, 7 degrees for the pitch, and 5 degrees for the heading. So I'm optimizing these 3 parameters, optimize all, maybe push it twice. Then I get a new an updated parameter. It's still not very nice. So what's wrong? So this means we are still having 1 meter offsets for the ground control points here, and some of them may be wrong completely, but there may also be a problem with the height of the system, flight altitude. So we can also go offset GPS data, and it tells us that we are 10 meters off. So for whatever reason, the height is 10 meters off. Another reason for this could be a wrong field of view. So the Shark import filter assumes a standard field of view of 29.5 degrees. Can you confirm that this is correct for your system? Do you know that?
20 meters.
20 degrees.
Yeah, 20. Is this degree or the height of this?
No, the field of view, the angle of the system.
20 meters.
In degrees, 29.
Yeah.
It's 29. It's 20 meters above ground. That's what I saw. Yeah, or 30 meters above ground, more or less. But the angle is. I'm not sure what. So you would need maybe the technical specifications of your system, because it could be that it's a different shark system than I had before.
Yeah.
But here I can just apply this 10 meters and optimize all again here. Here, update, optimize all, then I get 11 meters offset in the meantime. Update, optimize all, and so on. Now, now if you look over here, we are now in the range of maybe 10 centimeters offset, and some points are really weird. So, for instance, this one is 70 centimeters. So you so you could exclude the wrong points. So I could say, well, I just exclude all the points which have too much offset, so you can enter a value of 0.5 meters, auto exclude, and then optimizing it again without those points. So update, apply, and here also optimize all again. So you make the circle, you remove a few points, and in this way, at some point, you will get a bore sighting which is in a range of a few centimeters. You won't get to the 1 centimeter, to the pixel accuracy, because you don't have a digital surface model. So there's no way to get pixel accuracy with this data as it is currently. So that's the first thing. Now, what's puzzling is, after the bore sighting, it tells me that the pitch is in average minus 22 degrees. So the image is looking backwards by 22 degrees. That's kind of strange. That's not normal. So my problem is I don't trust in the orthophoto. Also, if I now taking. So I'm closing this bore sighting. I will show this afterwards. But first, if bore sighting is done, you have to save the status file, save status, and save this as bore sighting status, whatever, the flat or the other one, bore geo, such that you have these parameters stored of the bore sighting. And this one can always be used later for a regular processing. That's how it's meant. So you do this thing once, store the status, and use this status later for the processing. So it's only now going back into the problems. We have this 22 degrees offset, and if I'm now loading the bore sight, I'm loading the images, the one which is how far as I got so far. So I'm using that one. Band selection, the other way around. I'd rather like it that way. Okay. So this is the one which looks not too bad. It's not perfect, but it doesn't look too bad. But if I'm loading the auto, so the auto image, where is it? Group TIFF, the auto, I have an auto somewhere. Auto image, here it is. I also imported it to Envy. And if you compare these two, okay. So I can now check out if they fit to each other. You could do it in Envy. I don't know do you have Envy licenses?
Yeah. We already have. Yeah.
Yeah. So you could go also to Envy to do an overlay between the two, but it's very obvious here in the middle. So somewhere around here where we had the most ground control points. If I'm doing maybe this way around, so I can go do a push position and a get position. and it should go more or less to the same point. So I can also do a push position of this line here, and a get position here. Now you can't see it very well. It fits somehow, but it's not really good. So there is, maybe I can go a little bit further to the here, push position, get position. So it's already off by this a few centimeters, so 20 or 30 or whatever it is. And now I try to understand what the problem is, because in the middle it's more or less fitting. It's even worse if you go to the edges. So if you go to this panel here, I make a push position and I do a cast position. It's really off. So this panel is off in a long track direction upwards. Just remember that. So now this panel is upwards off. That panel down there, push position, get position, is shifted in the other direction. So now what could be the reason? And I thought, well, how to check this? And then I start to doubt the auto image. So if the auto image is really okay. So because this is very uncommon that you have in a long track direction once it's inconsistent completely. There's some inconsistency, and this should not happen. So what I did, I loaded the auto image to Google Earth to check it against Google Earth. And that's how it looks like. So here is the auto image loaded onto Google Earth. And so here is the Google Earth auto, and that's the other one. And that's really a big shift between the two. So I'm not sure if Google Earth makes a mistake when importing this auto, or if this auto was really, so if Pix4D didn't output the correct auto image. Another reason behind that could be a coordinate conversion problem, such that a coordinate conversion is somehow squeezing or doing a distortion in the data. So in short, it's based on this data. I don't see a way to get a better accuracy. So one could, well, using Google Earth directly is too coarse, as you see. So you cannot use Google Earth directly for this warsighting. It's yeah. I'm not sure. You said you're new to Pix4D, so maybe there was a problem, mistake when running Pix4D to create the auto. So that's something to check. Or you could also you provided a list of ground control points. This one.
Yes.
Have they been taken from the auto image?
Right.
Okay, yeah, then that's why it's fitting well to the auto image. So, and you didn't measure those.
We directly measured using GCP GPS station devices. So that is real value of the GCP point value.
So these values are directly measured.
Right.
Not from the auto image.
Yes.
Not, oh yes, it's not from the auto image, yeah.
Yeah, not used get the auto image. This is directly gathering of the value.
Okay, so these points seem to be okay. The only other thing I could imagine is that there was a timing problem with the sensor. Because this one fits well to the auto image. But
we use this value apply to Pix4D, and then we get an auto image.
okay, that's right. That's why the other image fits very well to these points.
Right, right.
Yeah. And this coordinate system of those is really the Korea 2020 coordinate system.
Right, right.
So, yeah, now I'm really struggling how to get this done correctly. This is the auto points. Why do you get? The only thing I could imagine is that the sensor is drifting, but if I'm looking at the auxiliary filtering, there's a slight drift in the roll, so it's going downwards. In the pitch, there's no drift at all, and what you see is a drift in the pitch. So it's on one side it's forward and the other side it's backward. That's a strange thing. And the heading is not a drift, or the XY coordinates. So we saw in the beginning that we have problems with the XY coordinates, that the GPS is not working properly.
I have a question about this graph. So what is a normal graph in the X or Y chord?
On the X, it's always the line. So the number of lines of the image. These are 5,800 lines in this image. So along track, the Y coordinate and the X coordinate, and the height of the system. So this is the and the so this could be, that's if the auto photo is really correct, then the only reason could be that there is a drift in the GPS, so the GPS is not working. Do you have an alternative GPS? Is this the GPS of the drone or the GPS of the sensor?
GPS from sensor.
That's from the sensor. Yeah. Do you have GPS data from DJI drone as well, or was it a helicopter?
Yeah, but we do not use the drone GPS data. We only use the GPS from Corning sensor.
One would need to. Has it been stored, the GPS of the platform? Is it a helicopter?
No, DJI drone.
It's a DJI drone.
Yeah, DJI M600.
Yeah.
Pro. Yeah.
So would you have somewhere the GPS data of the DJI 600 and the time tag?
I don't know. The sensor is automatically saved in their sensor devices. We only save the edge to other PC, like a IGN format file. So we only use that georeferencing use MB software.
Yeah.
So
yeah. So, but if you would have the raw data, the data stream of the M600 of the mattress, this would be an option to cross-check the GPS to see if there is a problem with the GPS in the Shark.
Okay.
The Shark has its own GPS, isn't it?
Yeah, they have the GNSS sensor already installed in their Shark devices. So
they don't take the data from the drone.
Yeah.
They don't. Yeah. So because I really, and we saw in the beginning that these jumps, so something's really weird about the GPS. So that's yeah. and even for the height. So there is something strange. And and I even have the impression, let me see the y coordinates. It's going such as if one would need to remove these gaps and go on straight or something like this. I don't know. You have a continuous measurement. So this could be the reason. Because the other IMU data look really nice, so I don't think that this is a problem. Well, it's not. It's a little bit too smooth, so it's very smooth. So it's apparently not highest frequency. If you look at it in short, you see it's quite over. These are 50 image lines, and it's a very smooth appearance. So this means maybe it's not measuring very high frequency, but it doesn't look bad. So that's what I'd tell about that one for the heading. Yeah, we see.
Where came from the data, XY core, the data in the Parge software? In this our raw hyperspectral data or fixed for the DEM file?
So I used your outputs. So I used the DEM data from Pix4D and the auto from Pix4D as you provided it. I don't have Pix4D myself. I can't do a reprocessing of that. One could, yeah. Okay. One thing I would maybe need to check is if the coordinate conversion in Parge for Korea is working properly. If there is a problem with the coordinate conversion. For this, could you? We have this data stream. So you have this. Where do we have it? Show text file. You have the XYZ in the nav file. I exported it to nav text long lat, that one. I searched that one. So this is the long lat, the input of the what we have from GPS. Here you also see that it's only measuring every 10 or 20 lines. So it's, and what I would like to check, I don't have another conversion tool for Korea. So would it be possible for you to convert this file to Korea coordinates?
Right.
This text, this long lat file, that's the output from the calling shark. So that's what you're getting there. And if you could convert this to the Korean system on your side, if you have some tools there, then I could check if Parge is doing the conversion correctly. Because that's one thing which can be checked as well. So I can send you this file, and then you could convert if you have. I guess you have something to do. It's good enough to have a few points, the first and the last point converted. I don't need the whole file if you have a point conversion available somewhere.
Okay. Could you summarize how to process when we processing orthomodal process using Parge software?
If you have multi-file processing.
Yeah. Could you summarize each of process using Parge software? Yeah.
For Shark, we don't have a full workflow implemented yet. So there is because for some we have this batch processing for the head wall and high map and high specs. We have this such that you can process whole directories. But for Shark, the problem is the stability of the system. So this full automatic processing can only be done if the system is stable. So, so for now, you'd have to import it manually, load. So through the menu, currently would be the process first import.
Yep.
Areas like that.
Yes.
As we did before.
Yep.
Second step would be import digital elevation model if it's not
MB.
there. So DM import. If it's a big DM, you can always keep the same, so you don't need to do that. So if it's still there. The third thing is control import offsets. Import offsets, so you would need the bore sighting file. So we take this bore, this thing. This would be the bore sighting GCS file, and then you could apply altitude and navigation offsets to that one, and so it then would import the bore sighting values such that it's calibrated. That's the third step. And the last step is you go direct to the maybe check parameters. That's usually fine. And you can go to the direct processor. So you can select bands all. Select all. Okay. Check if the elevation model, the elevation model could still be changed here, so you don't need DM reading before. Think about the target resolution. You could create an RGB JPEG preview. And usually I recommend using the fast nearest bilinear interpolation. So it does a compromise between nearest neighbor and bilinear. So original pixels are nearest neighbor, and in between pixels are interpolated. So that's a good thing. And then you can run it. So these are the 4 steps you need, or 3 to 4 steps. Import, bore sight, apply bore sight value, direct processor. These are the 3. Optionally, digital elevation model change or so.
Okay, but Corning sensor did not create the GCS data and files. So how can you generate the GSC files, both side files?
Yeah, after I showed you the bore sighting before with the ground control points, and you create it with file the save status.
Save status, yeah.
So these are the same. These files here are
Yes.
bore sighting files.
Okay.
These can be used for the import offsets.
Okay, I see. And then our project is using both camera, SpecSim, and Corning Shark. So is a similar process using SpecSim AFX 17?
AFX is better supported. So I will even add in the future a full process because it's better calibrated than the Shark. But for the AFX, it's import. I think it's also down. Let me see. Just a moment. AFX is not here. No, it's the import function is ISA Eagle Phoenix, same data format as Eagle Phoenix AFX. And Phoenix FX10 here is the format for the AFX ISA for the import. But I guess you for ISA you have the geometric processing from them, isn't it? If maybe you do it with CaliG, or if you need more calibration, you can do it with Parge. And there, usually the GPS is nice there, so you shouldn't have problem with that. With AFX, but with the Shark, it seems to be really strange. Yeah.
Okay. Could you share your output files, generate files to Google Drive?
Yeah, I can do so. I will send it to you. Yeah.
Okay, thank you. After I checked your output files, and then if I have a question, I send an email. Send an email.
Yeah.
Okay. Yeah. Thank you. Thank you, Daniel.
Thank you.
Yeah.
So we can.
I have one another question. We have many strip data each of area. So after I each by geo generation each strip, and then we have to all of strip have make a mosaic process. Uh-huh.
Yeah. Well, there is a mosaicing here in process, so you can do the mosaicing, so you can add whatever you want. Then you can do some mosaicing in Parge, and in these batch processing tools here, like for Nano or so. Well, it's a big thing, but they will do a mosaic automatically. So if once your system is stable, one can write a batch process such that all files are processed and finally a mosaic is generated. So this can be automated. If things,
Is it similar to MB mosaic, seamless mosaic, or pixel mosaic in the Parge mosaic process?
in this mosaic process,
Yeah.
it does based on it based on the real coordinates. So it's a coordinate mosaic, and it will resample to your target resolution, and it doesn't adjust the brightness. So because it should be you don't want to disturb the spectra. It's imaging spectroscopy, so you shouldn't change the spectra of the process. And but you could, if there are clouds or something, there is a possibility to correct for the brightness for cloud shadows. So you could calculate the so-called brightness map. And then there is a second thing, which is only available in the mosaic correction in Droit. You have the possibility to correct radiometrically below clouds and things like that. So usually you would do the mosaicing not in Parge, but after the mosaic correction. So it's better to do it then, because for that mosaic correction, you also want to process each image separately and finally do the mosaic of the reflectance data.
Okay, I see.
Okay.
Thank you very much, Daniel.
So can we conclude for today?
Yeah.
Yeah. So I guess we'll be in touch for further discussions, I guess, and then we'll see if we can work out where the problems are.
Okay.
Yeah. Yep.
Thank you.
Thank you.
Yeah.
Goodbye. Yep.
And I appreciate it if you share of your output of files to Google Drive. Yeah. Okay. Thank you, Daniel.
Goodbye.
Yeah. See you.
See you.
Bye-bye. Yeah.
Okay.